Okay, I think we can start now. So for today, we're going to talk about the exponential maps. To talk about the exponential map, we need to define a few other things first. So we want to define a vector field on G that is left invariant, and we want to define a particular one. Let's recall a few things first. Recall, let G be a Lie group. TEG is the tangent space at E. And this tangent space with the Lie group, with the Lie bracket is a Lie algebra. So let's write it like this. TEG. This is a vector space with a bilinear map. And this is called a Lie bracket. Okay. And also recall we can define a map called left multiplication. Just gonna abbreviate it. Let's write it like this: left multiplication by G. So fix an element. Fix G to be a group element. So left multiplication by G is a map from G to G that sends H to GH. Okay. Now we want to define the vector field. So given each element in the Lie algebra, we can define a vector field. So let's fix a x in G. And we can define a vector field Vx. We define Vx applied to G to be the derivative of left multiplication by G at identity applied to X. And I'm going to introduce another notation. It's just X subscript G. Okay. And let's draw a picture. This is G. This is the tangent space. And basically, let's say this is a vector. This is another point G. And this is the tangent space at G. And we're basically sending vectors.
Sorry. Is left multiplication the group operation?
Sorry.
Left multiplication, is that the group operation?
Yeah, it's group operation. I could write it down. Yeah, and that's the picture. So we have a vector field on a manifold, and what we can do is solve a differential equation. So we can consider the ODE. 5 prime of t is equal to dx of 5t. Oh, sorry, I skipped one thing. Let's. I should also mention that this vector field is left invariant. And what basically that means is xhg is equal to the differential of left multiplication by g at h applied to xg. And this is very easy to prove. We can just use the chain rule.
xg is a g, you're applying the differential h.
Oh. I think it should be this.
Is the final x sub g also a differential?
X sub g is this.
But on the bottom, sorry, maybe I just don't understand notation. You're taking differential first on h and then to g, but applied to x sub g.
Which is that? The DLH means differential of LH. LH is just a function.
That's good.
Okay. And I will write it out. So x of hg is equal to the differential of left multiplication by hg at identity applied to x. And then we can apply the chain rule, and that gives us the differential of left multiplication by h at g times the differential of left multiplication by g at identity applied to x. And well, this is equal to x.
Thank you.
Okay. So we have this ODE, and we're gonna gloss over some details. We're just gonna say that, like, oh, sorry, the manifold is smooth. So this ODE is nice enough. The solution exists and it is unique. Sorry, what am I looking at? Yes, okay. So we have a solution that's unique, and what I want to prove is that phi solution exists on all of R. So, and it is a group homomorphism. Oh, sorry. Identity. Okay. This solution exists on all of R, and this is a group homomorphism. And by the way, we're looking at R. Sorry, the group operation on R is multiplication. So this means sorry, addition. My bad. Addition. Okay. Right, here's the proof. So if you've taken a course in ODE, if the ODE is smooth, then you have local unique solutions. So suppose sorry. So let's just look at the solution on an interval I that contains 0. Okay, and we're going to prove this. So let's fix S and vary T. What we're going to do is we're going to define two things. Alpha of T, that is this, and define beta of T to be this. And we're going to prove that they both solve the ODE, and by uniqueness, they're the same. So let's define alpha of T to be phi of S times phi of T. And let's define beta of T to be phi of S plus T. We just compute the derivatives. Beta prime of T is equal to phi prime of S plus T. And because phi solves the equation, then this is equal to Vx applied to phi of S plus T, which is equal to Vx of beta of T. So beta solves the ODE. And and for alpha of T, we can rewrite it as left multiplication by phi of S applied to phi of T. And then so alpha prime of T is equal to the differential of left multiplication by 5s at phi of t times phi prime of t. And this is equal to since phi prime of t solves the ODE, we can write it as Vx of phi of t, but that just is the differential of left multiplication by phi of t at identity applied to x. And we can use the chain rule here, and this is equal to the differential of the composition of identity to x. Which gives us this, and by definition this is just equal to Vx applied to 5s times phi of t, which is Vx of alpha of t. Okay, so they both solve the ODE and they have the same initial condition. We can just check that, alpha of 0 is equal to 0 to the identity. Sorry, yeah.
You should check that anyone here has any questions.
Oh, okay. Does anyone have any questions? Okay. Yeah, we should check the initial conditions. So alpha of 0 is equal to phi of s times phi of 0, and phi of 0 is equal to identity. So this is just phi of s, and beta of 0 is equal to phi of 0 plus s, which is phi of 0. Yeah. So oh, sorry, phi of s. Yeah, and by existence and uniqueness, they are the same. Which, yes. Well, if the ODE is smooth, then you have a solution that's unique.
The question is not for me. The question is who have not taken this exam. Equal ratio.
Do I need to say more about ODEs?
Well, no, it's just, I have a general question. Like, what's the motivation between you? Is this an example, right?
We need this to define the exponential map.
You get you read the statements, you get the group homomorphism from the real line. Just from what did you use to construct this homomorphism? You used a single tangent vector.
Yep.
So the famous for every tangent vector, you can, which just gives you a direction. You can find unique group homomorphism from the line which goes in that direction. So the uniqueness is not necessarily.
That's a lot better, thank you.
Now we've proved that this is true on this interval I, where the solution phi exists. And then we're going to show that it extends to all of R. I'll just do this. Okay. Actually, I don't need a new board. I can just write it here. This statement itself just implies that it extends to sorry. Now we've proven that this is true on this interval I, and this proves that it extends to all of R, because let's say you have some real number x that's in R, like there exists n in n such that x divided by n is in I, and you well sorry, x. Oh, sorry. Yeah, it's just x. Yeah. So we've proven the claim.
To define it this way from the beginning, why do you need this condition? Why did you need to check this like
Wait, sorry.
to write down this definition?
Then how do we show that it solves the ODE?
Right, so you need to have checked what you just checked with the group law to first prove that this gives you a well-defined extension line. And also, yes, to show that it solves the
Sorry.
and also to show that the resulting extension also satisfies.
Well, this by definition satisfies the group law, right?
There's still a couple of things.
But it's not clear that the extension solves the ODE. It's not clear that the extension solves the ODE, and it's
You're saying, for example, why does this not depend on what n you choose?
that's true.
The answer is
Oh,
from group law.
sorry.
You need to do a couple of manipulations but we can all agree that we can all do those manipulations.
Yeah, I will skip over the proof that extending it this way means that it satisfies the group law. Okay, sorry. Oh,
Vaguely, why does this actually satisfy the ODE?
right. I did not think about this before. I think. Oh, I think it's sorry. phi is uniquely determined by phi prime at 0. By the first principle from last week. But yeah, let's say like phi satisfies this on R, then phi is uniquely determined by phi prime, because phi is a homomorphism from R to G. They're both, and then R is a connected Lie group. So it's just uniquely determined by the differential identity. We talked about that last time.
So there's a unique extension of the solution on I, but how do we know that that is a solution on R?
That is true. I don't. I'm not sure.
Maybe I could say it wrong.
Yeah.
Right. So you can imagine this: you have your group G, and you have the identity, and we found. So we took some direction x, and we found some small one parameter family which solves the equation and goes in this direction. And what we've proved here is that if we take this small family and we translate it in time, or equivalently, we just multiply it. We take some point on this segment and we multiply this whole segment by that point. We translate it along the group, so we get some translated segment like this. Then this also solves the equation. This is what this what they proved here, right? So what we can do is take our small interval and then translate it in time, then translate it again, then translate it again, until we just fill the whole line. So we'll translate it here, then we'll translate it here, so just having a solution on a small interval gives you a solution on the whole line. But this, well, this is just a formula that is convenient to write down. But really, the idea is that if you have something, that this equation is special, that its solutions are translation invariant. So you can utilize that.
Okay. And I would like to make a remark, which is so phi of x, sorry, phi sub x, we should write is uniquely determined by the fact that it is a homomorphism from R to G. Group. I'm going to abbreviate homomorphism from R to G with it where its tangent vector at identity 5 prime x is equal to x. And this is just by first principle from last time. Okay, I will just write it down. What we said last time is let G and H be Lie groups. G is connected. There's rho from G to H is uniquely, this is a group homomorphism, is uniquely determined by d rho at identity from the tangents, which is from the tangent space of G at identity to the tangent space at identity of H.
I'm just surprised because usually this is proved using your remark, and not the other way around.
Oh.
What was the idea of the proof?
Strictly speaking, there was no proof given. They said we'll do it later, and then never did it in the chapters I was covering. So maybe this might be circular. Do you do this later?
Oh,
Your remark, you don't need to use anything strong like this, because this is just well, not
I did not prepare this to like prove it directly. So we can come back if we have time. We're gonna cover this work. Maybe, okay. What should I erase? I'll erase this. And then we're going to make two definitions. It's phi x that solves the ODE phi prime is equal to Vx of phi x and that initial condition. From R to G, this is called the one parameter subgroup of G with tangent vector x at identity. And then another definition that we're going to make is the exponential map. It's a map from tangents, which is also the algebra to G, and the map sends x to phi x at 1. Okay. And there's a property. Note that phi at phi subscript lambda x of t is equal to phi x of lambda t. And the proof is by uniqueness, because it's uniquely determined by phi prime at 0. We're just going to compute it and show that they're the same.
What is lambda?
It's just a real number.
And x is an element of the Lie algebra.
Yes.
Yeah, sorry about that. Okay, thank you.
And for the other one, we compute d dt at t is equal to 0 of lambda t. This is again like chain rule. 0 times lambda, which is equal to lambda x. And then by uniqueness, they're the same. Okay, and then we're going to do an example first. We're going to compute like an explicit formula for the exponential map for G is equal to GLN. So let's start with like why is that? let's write down a chart first. So we want yeah, and this should be a subset of U. So we I'm going to write down. Sorry. Phi inverse is from U to GL and R, and it sends Xij to Aij plus Xij. Yes, wait, what is that function? And we can choose a small enough U such that is the image of U under phi inverse is contained in GL and R. So,
We don't really know the chart for Q and R because it's not trapped. It's open inside the vector space alone. But
oh, that's true.
you're doing some sort of translation.
You can just, yeah, because you could just take identity and it's like phi to be identity and it's.
Your chart, the principle could be your U could be all of G and R except translated by Aij.
Right, so there isn't really a point to this. Maybe I should just say. Open. And this is because, let's just show the complement is closed. So the determinant is a map from, I mean, n by n matrices with real entries. Sorry. Yes, n by n matrices. To R. And then the claim is that this take away GL and R is closed because this is right. It's a matrix is in GL and R if and only if it has non-zero determinant. So this is zero determinant. So that's the like pre-image. The pre-image of of zero under the determinant map. And this is a continuous map. So this is closed. And so this is open. Okay. And then we can look at the vector field. It's evaluated at A, and that's the differential of rest multiplication at identity times x. And well, left multiplication by A is a linear map, and the derivative of a linear map is itself. So this is just equal to A times x. Yeah. So our differential equation becomes sorry. Should I have done right multiplication? Should I have done right multiplication? Because I realized that there's a problem. Because if I want the solution to be e to the xt, then my ODE has to be phi prime is equal to x on the left times phi. Oh, they can meet?
Yeah, because E big xt, you can mention it as series in x. Right?
Yeah.
It's a series where every term is just something with x.
Oh, I see. Yeah, I see.
Sorry.
Yeah. Okay, I see. Okay. And the solution to this ODE is phi of t is equal to e to the xt, which is defined to be yeah. Yeah. Do we need to check that the derivative is equal to x times e to the xt? Or are we good with that? Oh, right, I need to.
N factorial.
Yes, it's n factorial. The equation looks the same as like the Taylor series expansion for just e to the a real number. Yeah. Okay. To check it converge, I need to introduce matrix norm.
No, it's just what is convergence for objects in effect, or what's
Well,
convergence?
it converges if the norm converges. So you can define a norm on a vector space, right? I think the norm of x is defined to be the supremum of so v is in S n think that's like this.
I think divided by norm of v.
No, v is an Sn. Sorry.
Yeah, sure. Okay, that's it.
Yeah.
So you need to fix norm vector space. And then you just look at the unit sphere, the maximum of how much x can stretch the vector sphere. That is the norm.
Um. Okay. So I guess you should consider norm of this, which is and this there's a property. I don't know. I'm not going to prove this property, but the norm of AB is less than or equal to the norm of A times the norm of B. Oh wait, this was covered in 247, isn't it? I think.
It's not in a familiar form, but you know.
What was it? I don't remember the name of the inequality. Do you remember?
Cauchy-Schwarz.
Oh yeah, Cauchy-Schwarz.
Yes, you could say it was
Cauchy-Schwarz X94.
I think Cauchy-Schwarz is like 5.
So this is
I don't see how this is Cauchy-Schwarz.
This is not. Well, it's adjacent. You're supposed to take the norm of the inner product.
Right. This becomes Cauchy-Schwarz, but not if A and B are not square matrices. It's Cauchy-Schwarz if A is a row matrix and B is a column.
Okay.
But for square matrices, follows, or for any matrix of any rectangular shape, it just follows straight from the definition. So the supremum, double supremum is greater than supremum.
Are we asking what it converges to, or if it converges?
well, I'm gonna show that it converges for all matrices. This is sorry, less than or equal to. And this is equal to if you take in 157, you should know how to prove that this yeah. So it converges and sorry, yes, it converges absolutely.
Series of the norms converges, and the series in vector space is called convergent absolutely, and therefore by Cauchy's criteria, the series itself converges. But if you don't know all of this, then maybe you can just believe that this converges, and that the exponential on matrices is defined.
And then you can also check that phi prime is indeed equal to sorry, d dt e to the xt is equal to x times e to the xt. It's just a simple limit computation. I don't think I need to go over it. Okay. I'm gonna have one more thing prepared. Okay. So the exponential map is the unique it's a unique map from the algebra G to the Lie group G that sends 0 to identity, and I'm going to use uppercase. The differential at 0 which will be from the tangent, which is equal to this, because it's a vector space. To and this map is identity. Yes. There's one more thing. Restrictions to lines through sorry, what is it? Components. Oh, sorry. Through the origin. In G, the Lie algebra are one parameter subgroups. Okay. Let's start with the most obvious one. 0 gets sent to E. That's pretty obvious. Okay. The next one is let's show that the differential is at 0 is identity. Okay. Now let's look at DDV. Apply to V. And that's just equal to ddt exp tb. For some, this b is fixed. And then we can use the formula from before, which I just erased. So this is equal to, we know that this is equal to phi tv of 1. But this is also equal to phi v of t. So it's just the derivative of with respect to t of that, which is equal to sorry. Wait, I forgot one thing. Sorry. T is equal the derivative of t is equal to 0. Is equal to b. And that shows this. And this uniqueness. In my notes, I also wrote uniqueness follows from the first principle, because you could also consider like G, the Lie algebra, as a Lie group. It's a vector space? Wait. It's a vector space, so it's a manifold.
The exponential map is not.
Oh, sorry.
For one, the vector space small g is Abelian. G might be non-Abelian. You did say that the restriction to every line passing through the origin in small g is a group no longer. But the whole map follows value.
I see.
Now that you've proved that the differential is 0 is the identity, if you want to know what that map is at some elements x of g, you just need to draw a line x and 0, and in fact the map is uniquely defined on that line, because you know that the one parameter subgroup is defined by this.
Oh, I see. Okay. Yes, okay, I see. So the uniqueness follows from the uniqueness of phi that solves the ODE. Yeah, and you just draw a line like Ruslan said, from the origin to any point. And then on that point, this phi is unique, so the exponential map is unique. And I think basically the last part is a restatement of what we said before. We defined, like, phi is basically the restriction of the exponential map to a line. And we defined it to be that way, so yeah. That's all I have prepared. Is there any questions? Okay.
Can is something we did not prove.
Oh, true.
The uniqueness of one parameter subgroup. And I can not sure how to prove it. I can say because
Sorry.
thank you. There are two statements that need to be proved. And the first one is easy. It's the statement that given a vector x in your Lie algebra, by the way, in the type pulse, the Lie algebra is usually written like this. But Right. So given a vector in the Lie algebra of a Lie group, there exists unique homomorphism Dx from R to G satisfying the initial conditions. Okay. This was stated, but it wasn't proven, but it's easy to prove because, well, suppose that, actually I'm not even sure, I think you can do without the principle of exclude needle here, but okay. Suppose that you have two such homomorphisms. Then, well, actually both of them are solutions to the same differential equation. Because you know that phi x, the derivative of phi x at time t is your left invariant vector field. This, phi x. And the derivative of your vector field C is also the left invariant vector field. They're at different points, but that's not a problem because you see that, right? You see that both of these curves in G solve the differential equation phi dot equals x, and they both have the same initial condition. Therefore, they are the same. Right, except maybe you're wondering why they both solve this equation, and that is because what is this phi dot x of t? It's d phi x at the point t of the vector d dt in the line, right? And then and this vector at the point t is just the left translation of this same vector at the point 0. And now you use the homomorphism property to pull that left translation through the homomorphism and get this equation. I suppose that wasn't too clear.
But I don't think the left translation.
Right, that's just it's a vector on the line. You have the real line, and you have the parameter t here.
Oh, so it's
and this is the unit vector. Yes. Okay. So differentiating along this vector field just differentiates a function in T. That's why it's called this. Right. So, and then you would agree that left translation by T on the line is just, well, translation, additive translation on the real line. So in fact, if you take the unit vector at 0 and translate it by T, you get the unit vector at T. Right. And then the homomorphism property implies that well, it's not enough space. Implies that the diagram from R to R to G, where here you have LT and here you have LP of T. Here you have your map dx. Here you have your map dx. But this diagram is commutative, and therefore you can exchange these two and get instead dl dx of t of at e and of d dx at e at 0 of x, which is just the left translation of the vector. Sorry, and this is just x by the initial condition. And so you will just left translate x, and you'll get x at the point dx. Anyway, I don't know if you didn't get this technical explanation. Yeah, any questions about this? It's a proof. And you see how it uses the group homomorphism property.
Can you explain why the diagram?
Well, you can't see anything that's written here because it's a mess of things. I think there is the recording. I don't know. Meeting was ended. So the diagram was R goes to G, goes to R, goes to G, where both of these maps are your homomorphism to X. Homomorphism by assumption. And here you have just a left translation by some time t, and here you have a left translation by dx in the group. And why does this compute? Well, this is just the homomorphism condition. Because what is this composition? It's you need to take some time s here, you need to apply px to it, and then you need to multiply it by px of t. So this composition gives you dx of t, because you multiply it by it on the left, applied to dx of s, because this is what you got here. And this composition will give you, first you translate by t, so you had s, now you have t plus s, and then you apply it to dx, so you get dx of t plus s. And the equality between these is exactly the homomorphism condition. So in fact, right, so we can package the condition that the map is the homomorphism into this commutative diagram, then take the differential of everything, and then use that to prove the differential equation holds. Right. That's the first thing. Any other questions? I don't know if I can. It's not that important. The second thing is what was called first principle. Not that I've heard anyone call it that. Sometimes called Lee's first theorem. But okay, anyway, the statement is if G is a connected Lie group and H is any Lie group and you have two homomorphisms such that they agree to first order at the identity. So E of E and E of E is the same as E of C. These are the maps between the algebras. Right, this is just my notation for the differential and the identity of this is the differential. Right. Then phi equals C on all of G. Okay. So again, the statement is a group homomorphism from a connected group is determined by its differential at the identity. And why is this? Well, the whole proof is actually not straightforward. Well, it is straightforward, but it has a technical side. There are two steps for it. Right, yes, two steps. And the first step is you need to show that there exists some neighborhood of the identity in G on which the two maps agree with each other. Okay. And this is actually easy because this follows from what Ife proved today. It's about the exponential map. Because we know that the exponential map from the Lie algebra to the Lie group has differential 1 at 0. Therefore, by the inverse mapping theorem, it is locally invertible at the identity. So this is there this a U such that U containing identity such that the exponential map inverse from U to G in the algebra is well defined. This is by the inverse mapping theorem. And now you know that, so this tells you that every element in U is the exponential of some Lie algebra elements. Well, now that you know that, you can utilize what I just raised about the uniqueness of one parameter subgroups given by their direction and identity. And so every group element in U is the exponential of some Lie algebra element. Then what I just raised tells you that phi of such a group element G is just the exponential of the differential and the identity of phi applied to X in H. And this is the same as C. Right, this is just this holds because the exponential map gives you a one parameter group in G. The G is H, and you have a one parameter subgroup in G. It must map under the homomorphism P to a one parameter subgroup in H, because a composition of two homomorphisms is a homomorphism. And we know that under C, it also maps to one parameter subgroup. But since P and C agree to first order at the identity, the directions at which these two one parameter subgroups in H go coincide. So they're actually the same one parameter subgroup. So in fact, all the points to which you can get along the exponential map, you already know what their images are. They're the exponentials of the corresponding tangent vectors at the identity. The only problem now is that, okay, now you know that your maps agree at U, on U, and in fact they agree on all the points to which you can get via the exponential map. But the exponential map is not surjective in general. So the problem, the exponential map from G to G is not surjective. It's an exercise for you to think of examples when it's not surjective. Right, and why is this a problem? Because we can't just take an element in G, take some Lie algebra elements such that this element is the exponential of that Lie algebra element, and push forward the Lie algebra element and take its exponential in H. Because the map is not surjective. So the second step we take is to prove that U is a group.
We did this last week.
Oh yeah.
Yes.
So we skipped the hard part.
Maybe this is not as hard as I remember. If you did this last time, what is the proof?
It was just showing that.
Oh, showing that something is, yeah.
Yeah.
Fair enough, because you can always translate this set.
Yeah, pretty much.
That's fair. Okay, so it generates G as a group, and now you're ready to prove the whole result, because you know that the two maps agree on generating sets, therefore they must agree on the whole group by algebra. And so now you've proven this theorem. You proven this theorem. So unless someone wants to prove something else.